Now let's talk about the continuity of a function. Function is continuous at a. That means, again, x equals a. There is no whole, jump, or asymptote at a. Think about it as being able to draw the graph without lifting your pencil. Let's take a look at the first graph over here. In this graph, there's a hole at x equals 2. Even though it is defined at x equals 2, here at this other point, and the limit would exist at x equals 2, the graph itself is not continuous. In example B, there are jumps. We obviously cannot graph that without lifting our pencil. Also at C, you have an asymptote. It looks like it's here at x equals 0. You would have to lift your pencil after drawing the left branch in order to draw the right branch. None of these functions are continuous. To say that f is continuous at x equals a implies three things. First, the function value is defined or exists. 2, the limit as x approaches a of f of x exists. And most importantly, the limit as x approaches a of f of x equals f of a. So again, we could draw the graph without ever lifting our pencil. This is continuous. If we were looking at some x value of a, the y value, or f of a, exists, and the limit as we approach a is f of a. Now there are 7 functions that are continuous on their domain. They are polynomials, rationals, radicals, exponentials, and logarithms. Also trigonometric and inverse trigonometric functions, but we will not be covering those in this class. So it helps to know the domain to determine where it is continuous. In example A, we're asking if the function f of x, which is 3 of x plus 5 over x minus 2, is continuous over the following intervals. The first thing we need to note is that this is a rational function, a fraction. And since we cannot have 0 in the denominator, remember anything over 0 is undefined, which tells us x cannot equal 2. In A, we're asking if it's continuous over the interval from negative infinity to 2. Notice 2 is not included, so yes, it is continuous. In B, it's going from 2 to 7, but notice that 2 has a bracket. That means 2 is included, therefore it is not continuous over that interval. C, 2 to 10, 10 is included, but 2 is not. So we're safe. And then in D, the 2 is included again because of the bracket, so it is not continuous over that interval. Now in example B, we're dealing with a piecewise function that has a different domain for each piece. Before we look at these, let's consider where a piecewise function may not be defined. Suppose, and I'm just making up a graph, so suppose we have this part of the function, perhaps this part of a function, and this part of a function. So notice the domains on each of these pieces of the function, they overlap. Here at x1, it's not included here, but it is included here. The question is, does the limit exist at x plus 1? And is it continuous at x plus 1? In order for it to be continuous, not only does the limit have to exist, but it has to be the actual function value at x equals 2. So at x1, it's not continuous. At x2, it is. It overlaps. Anywhere else on that graph, it's going to be continuous. So let's take a look up here at example B. They're asking us about x equals -4. Well, -4 is in this domain at the very top, and it's not an endpoint of that domain. We can plug in -4 into that line, and it can absolutely be continuous interval for the domain. So yes. In other words, that would be like choosing a point down here. Is it continuous at this point on that piecewise domain? Sure. So now let's look at B. B, we have to be more careful because notice it's at one of those endpoints. Does it have two different endpoints, like this part of the little example? Or does it overlap and have the same endpoint and therefore be continuous? We have to check. So let's plug it into the first part. 3 times 1 minus 2 would give us 1. And let's plug it into the second piece, and hopefully it will overlap. We have a -1 plus 2, which also gives us a 1. Since they're the same value, that means they have the same limit from both directions, and therefore it's continuous. In C, we have x equals 5. That is our other endpoint of one of those domains. So we have to plug into both. If we plug it into the second one, we would get the opposite of 5 plus 2, which would give us a -3. And then plugging it into the second one, we would get 5 squared, which is 25, which means from the left side of 5, we're getting a -3, but from the right side of 5, we're getting 25. The limit does not exist, and that means it is not continuous. The very last one is x equals 0. And again, x equals 0 is completely within that top domain. So yes, it is continuous.